So we know that antenna can be represented as essentially a load impedance for a particular transmission line that is feeding RF energy into that antenna. This situation can be equivalently represented as a transmission line with a certain load, which ZA is being the antenna load. So those are the impedance characteristics of the antenna. Now we are going to look at what are called as the radiation characteristics. That means this antenna, after it has accepted certain power, how this is going to radiate into space. And it is going to radiate in general into three-dimensional space, in all the three dimensions in entirety. For example, if you see the antenna to be of this sort, it's going to be this dotted surface is going to be a spherical surface. So it's going to be radiating in three dimensions. So that radiation mechanism, how the radiation characteristics are going to be, are quite different when it comes to the space surrounding the antenna, depending on how far that space is from the antenna. For example, that distance df, if the point that we are looking at is less than that distance df, we call that the radiation characteristics are in the near field of the antenna. So in the near field, the energy is going to be pulsating, going back and forth into the antenna. So back and forth into the antenna, and it is a reactive energy, meaning that it is not flowing out. Whereas for any point outside DF, which is beyond DF, is what we call as the far field, where the radiation is radiative. Yeah, the energy is radiative. That means it's propagating in a certain direction. So this DF depends on the type of antenna that we are looking at. For aperture antennas, where the maximum dimension is D, this is the physical dimension of the antenna, this is the physical dimension. For such cases, the distance where you separate the near field and the far field, the DF, that distance that you separate the near field and the far field, is estimated to be 2D square over lambda. It is given as 2D square over lambda, where it is a function of frequency captured by the wavelength here, as well as the physical dimension of the antenna. So what is interesting in the far field is that the electric and the magnetic fields, are related by the so-called intrinsic impedance of the free space or air or the medium that we are having here. That means, what do we mean by that? We know that electric field is in volts per meter, the magnetic field is in ampere per meter. So the ratio of the magnitude of the electric field over the magnitude of magnetic field is something like an impedance quantity, and that impedance is what we call as the characteristic impedance eta, the Greek word eta naught, and this is equal to 377 ohms for free space. In fact, this eta is going to be square root of mu naught over epsilon naught, where mu is the permeability of free space and epsilon naught is the permittivity of free space. These determine the material property of the medium. It depends on the material properties. So in general, we see that in the far field, the electric and the magnetic fields, they are related in this manner of 377 ohms. Not only that, turns out that the electric and the magnetic fields, they decay over at the rate of 1 over R. The electric field is proportional to 1 over R, and so is the magnetic field, and it is proportional to 1 over R. So they are decaying as 1 over R. And if you look at the power term, power is going to be something like E times H, is going to be in a complex form, is going to be the conjugate, but in general it's going to be voltage times current. So to draw an analogy, it is like voltage times current. Very similar, it's going to be E times H, meaning the power in the far field is going to be decaying at 1 over R square, meaning that as I move away from the antenna, my power is going to decay 1 over R square. Now there are two important parameters that we need to know when it comes to the radiation characteristics. One is how the pattern of radiation is going to be, and second is the polarization. We know that polarization is the direction of the electric field. So an antenna is going to radiate electromagnetic energy. Out in the far field is the electric field, and that electric field is a vector. The direction of the electric field is what we call as the polarization of the antenna. So the direction of the electric field that is radiated by that antenna is what you call as the antenna to be polarized, to have maybe it is linearly polarized or circularly polarized. We will see what that is in another video. But the other important aspect is the radiation pattern, which we need to go and look into how the antenna radiates in 3D. And for that we need to look into what is called as the spherical coordinate system. Spherical coordinate system, where the origin or the center or the origin of that coordinate system is the antenna itself. Meaning that if you have an antenna here, it is going to be radiating up maybe, then we need to look at how it is going to radiate in that three-dimensional space. That is called as the radiation pattern of the antenna. And instead of looking at the electric or the magnetic fields, we are looking at what is called as the power. So what we are looking at is the power pattern. That means how much of power is the antenna radiating in this particular direction, which is going to be proportional to the electric and magnetic fields and going to be decaying at 1/r square. What is interesting to note in terms of the electric and magnetic fields is that once we move out of the near field and once we move to the far field, we notice that both the electric field and the magnetic field, they are a function of theta, phi and r. They are functions of theta, phi and r, and of course this r dependence is now captured as 1/r, and for theta and phi it can be different for different angles of theta and phi that we are looking at. Important thing is this E theta and H theta, once we move to the far field, is not having any ER component or HR component, does not have any component along the radial direction. That means the electric field has only two components, the theta or the phi, depending on the polarization of the antenna. The radial component is always 0. And this electric and the magnetic fields in the far field, when we combine them together, we get the power pattern. And so this power pattern is expressed in dB, so it's going to be 10 log 10. Being a power pattern, it is going to be 10 log 10 of the power pattern in linear terms. So this is going to be the power pattern in dB. So this three-dimensional plots, depending on how the antenna radiates, we can classify them into two types. One is isotropic and the other is a directional antenna. An isotropic or omnidirectional, meaning that the antenna can radiate at the same intensity in all the given directions. That is going to be an omnidirectional antenna. It's radiating same. That means the spherical surface is what its radiation pattern is going to look like. It's radiating the same strength in all the directions. So typically you would want a mobile terminal, user terminal, the UE for example. The user equipment needs to be having an omnidirectional pattern, because we never know how we are going to orient the antenna while we need to talk to the base station, how we are holding it, in what position we are holding it. Regardless of how we hold it, we should be always be able to receive in any direction, and we should be able to transmit in any direction. The base station could be anywhere. The other category is what is called as the directional antennas, where the pattern is in a particular direction. Depending on the application, you might want to have an isotropic or a directional antenna. For example, radar applications, like example a car radar application, if it wants to avoid collision, the car is supposed to be looking at, maybe while it's moving at a high speed, to avoid a collision it should be forward looking. So the antenna needs to be looking only in the forward direction. It need not be looking in the side. Yeah. So in that scenario you would want to have something like a directional antenna. So the radiation pattern needs to be understood, how the radiation mechanism works, and in general it is going to be a three-dimensional pattern where you have the X, Y and Z in spherical coordinate systems. It's going to be theta, phi, or elevation and azimuth. Elevation and azimuth are two different ways of specifying which location which angular quantities at what angles that we are looking at a particular direction, what is going to be the power that is received there. But it is hard to see three-dimensional plots like this, and typically polar plots or rectangular plots, these are two-dimensional plots, 2D plots of the three-dimensional phenomenon, which are essentially the cuts that cuts maybe the XZ plane or the cuts in the XY plane are plotted in 2D to better understand how the radiation occurs. For example, here that you see, we are having a pattern that is looking like a single lobe here and a back lobe, which is actually the XY plane. So this becomes the XY plane, and the XY plane is where the azimuth changes. It is the azimuth angle that is changing here, so we call this the azimuthal plane or azimuth. Whereas here, this is the elevation plane, or rather the XZ plane, the XZ plane. So this is like a polar plot in 2 dimensions. Alternatively, instead of plotting it in polar, we could also have it as an angular quantity, as an angle. Could be the azimuth angle or the elevation angle, depending on which cut we are looking at, and that could be a rectangular plot, and what we are looking at, the strength of the signal in what we call as the directivity of the antenna. We will see what that is later on, but in essence, the rectangular plot captures what is the strength of the main lobe, how much is the side lobe. For example, this guy is the side lobe here. How much is the level of the side lobe relative to the main lobe, so that it doesn't pick up any signal in this direction, but rather picks up the signals in this particular direction. So for example, if you see this kind of pattern, the antenna is not going to receive any signal in this direction because the received signal strength is minus 40 dB or minus 30 dB, much lower, whereas it's going to receive a very strong signal here. So this pattern is pretty useful to understand the radiation plots of an antenna, and depending on the application, we can look at the data sheets, look for the directivity pattern, and decide on what kind of antennas will be suitable for the particular application that we are looking at.